Monte Carlo simulations have been around for quite a while in classical computing. Since 2015, the quantum computing industry has believed they would be one of the best use cases to show quantum advantage. QC Ware was able to prove the feasibility of this approach recently, working with Goldman Sachs. And now they want to share that field-tested approach, along with other use cases, in a powerful tool. Find out how to get access to proven, reusable code in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. So our guest today is the head of business development for QC Ware, Yianni Gamvros. Thanks for joining me.
Thanks for having me. Glad to be here.
You want to start by maybe telling my listeners a bit about QC Ware?
Yeah, sure. So QC Ware is a software quantum computing startup. So we build software that runs on quantum computers, and the whole value proposition for the company is that we will help companies essentially get ready for the potential upcoming quantum computing disruption. So quantum computing has the potential of really disrupting everything we do today in data science, everything we do today in AI and ML. And there's already there's already a lot of anxiety that's starting to build up around this topic, around which use cases are going to be affected, and how exactly the different companies need to be prepared. And QCware's mission is to help these companies essentially get ready for that upcoming disruption, figure out what parts of their businesses are going to be affected, and how to best make use of these quantum computers.
Excellent. Yeah. And I was looking into you guys, and I noticed that in addition to the work you do, I'm going to get to in a little bit, you actually provide a way for people to do some of this themselves, right? So you want to tell me a little bit about Forge?
Absolutely. So Forge is essentially one big area, or one big way that we go to market by building the software product called QC Ware Forge. The other one being our consulting services, which maybe we can get to in later. But Forge itself, the easiest way to describe it is that it's basically like a data science platform that runs on a quantum computer. So anything that you would do today on a data science platform, like, let's say, running a classification algorithm, running a clustering algorithm, running a neural network, you could do on Forge today. But the algorithm behind the scenes that runs on the platform is actually a quantum computing algorithm. It's an algorithm that can run on a quantum computer. And you have the option on this platform to either simulate the execution, so simulate on a classical computer what a potential quantum computer would be doing, or actually run on real quantum hardware. So you can do either or. Essentially, you provide the same kind of inputs you provide to a typical data science platform. So a data scientist would come up with a data set, with a table, and let's say what you're trying to do is a classification or a clustering of your data points. Essentially, you're providing this to Forge and then selecting one of the algorithms, one of the APIs that's currently available on Forge. And then you will also be selecting an appropriate backend and saying, I want this simulated, or I want this to run on a real quantum hardware. Once you specify all that, then Forge takes all that from you and then goes out and either does a simulation or runs on the quantum hardware and returns back the result.
Yeah, one thing that immediately leapt out at me was this idea of no prior experience necessary for with quantum computing. So are you then providing really sort of like abstracted building blocks to creating a circuit?
Right. So the way that I explain it is that actually we have two main types of users. The one type of user for which the workflow is the one that I just explained, right? The classical data science user that actually doesn't really know or doesn't care so much of what happens under the hood, right? Because in the typical workflow, the typical data science user doesn't really necessarily know how, let's say, a clustering algorithm works, doesn't necessarily know how a classification algorithm works. They just want to have a good implementation of potentially one or more of these classification algorithms or these clustering algorithms, and they provide their data set. They get back a result, and maybe they want to tune a little bit the algorithm with some parameterization. Maybe they want to tune a little bit their data set and kind of try to make the algorithm work better or come back with better insights. But they don't spend any time actually going out and actually building a new classification algorithm or a new clustering algorithm or something like that, right? So that's essentially the one main type of user experience and the main type of user that we accommodate on Forge. However, the other type of user is a little bit more sophisticated and sort of peels back the one layer of the onion. And for that user, we say, well, let's just assume you have some quantum computing experience. You're a quantum engineer or a quantum developer, and you want to build something that's highly customizable or highly bespoke for your specific use case, but you don't want to build everything from scratch. You don't want to kind of essentially reinvent the wheel. You want to get some of the existing features that we've already developed, existing quantum circuits that we've already developed. And so we make those available to you as building blocks, essentially a quantum code or quantum circuit, as we say, building blocks, right? So we give you these quantum circuits, and then you as a quantum developer can use that block, then build a little bit on your own, then use another block, and keep going like that, interchanging those things until you end up with something that's kind of very unique for your problem.
And do you have to select the backend target before you start doing this kind of like drilling down under the hood, or is that selected later? Like, does it change the experience or how you code it?
Right. It's not. There is no really difference in how you code it, and actually that comes from the fact that essentially the value that we provide as QC Ware and the value that QC Ware Forge provides is this in these algorithmic building blocks that are sitting essentially very, very close to the end user, very, very high in the stack. So if you consider the entire stack all the way from essentially the end user sitting at the very, very top, then comes this layer of applications and algorithms from QC Ware Forge. Then come other middleware layers that typically go out and take an algorithm, take an initial circuit, and then translate it across different potential backends. And then come the different backends, the simulation backend, the different hardware vendors and the different hardware architectures, right? So we're sitting very at the very top of this stack and very close to the end user. And as a result, we can create this algorithm or algorithmic building block or circuit building block, and then the rest of the stack that we use, which actually comes from our partners, can essentially disseminate that to the different backends. So initially, when the user starts coding, they can say, "Oh, I'm going to use this building block, or I'm going to use this algorithm," and then later on, they can say, "Okay, I'm going to define now which backend I'm going to use, and I'm going to get now the results."
So you then handle it all the way. It goes from Forge directly to that backend target. It's not like you have to take the code and paste it into some other environment or anything like that. It's
right. It's exactly all of it happens in Forge. But again, I want to be absolutely clear that essentially our value proposition is providing you with these
Sure.
end-to-end algorithms or the algorithmic building blocks. Actually, taking it all the way to the hardware comes from us having integrated Forge with some of our partner solutions, and specifically, we've partnered with Amazon Bracket, and so we essentially send the circuit that we want to execute to Amazon Bracket, and then Amazon Bracket, and we also tell Amazon Bracket, oh, we want to execute this on a certain hardware vendor, and then they actually complete the rest. That's kind of the part that they add. So that part is coming from Amazon Bracket, our vendor, but we are integrated essentially with them, so the user doesn't have to copy paste anything. They can just stay in that same environment and same workflow.
Yeah, so you just like create an account and it ties in with API keys or whatever to what you're already paying for, and then they can just go in.
Yeah.
And is there any kind of like way to control that for multiple users, like to have like controls on how much money they spend or anything like that?
Right. So we started building actually Forge maybe 2.5, 3 years ago, and actually that was one of the big things or the big requirements we were faced with right away, because all the customers that are using quantum computing right now are essentially large corporations, R&D departments, and large corporations. Those R&D departments work with many different business units, many different researchers, sometimes external even to the corporation. They might be working with some academics or some other groups. And so there was already from the start a very strong need to have this being offered essentially as an enterprise solution, where you have administrators that are essentially are controlling who gets invited into the account. Many different people need to get invited. There needs to be some user management, user control from the administrator side, and also how many resources can each group or each individual user can they spend. So there's already also these constraints that the administrator for a certain enterprise account can set on the different types of users in different user groups.
Excellent. And I was looking what's there now. There's optimization, machine learning, linear algebra, but you have Monte Carlo simulation coming and chemistry. And I consider simulation to be one of those big three, right? You've got your optimization, your machine learning, right, and your simulation. So I guess, are you then taking some of what you're learning on the consulting side, like from what you've done with Goldman, which we'll talk about in a moment, are you taking some of that and then like adapting it to the Forge tool, bringing it to the masses kind of that way?
That's exactly right. I mean, that's exactly the whole business model, is to essentially execute several of these consulting engagements with large strategic customers and take the lessons learned and essentially distill them into the product and take the product essentially to the market, take the product to, a bigger market, a wider market, and have that wider market essentially benefit from what we found in those strategic lighthouse engagements.
Nice. Yeah. I feel like I end up asking this kind of often, but so now we've got what you're feeding into it as, code that people can run. Are any of your users also sharing then? Are they also providing like solutions to problems, like especially the quantum engineers that really like drill down? Is any of that then being shared with future, people with less experience who come to the tool? Or
Right, that's a good point. But no, actually, we're not set up for this kind of community building. This is really we're targeting this for enterprise use and performance use and competitive use. So I feel that kind of most of our customers wouldn't actually be potentially interested in that, or I don't see Forge as the right environment to do that. I can definitely see many other environments, right, where there's a need for that to offer essentially some code for reuse. But Forge is not really built for something like that.
Okay, so right now, if you're a user, then you're getting the benefit of your team's code that you create.
Exactly.
Okay.
Exactly.
And that's, I guess, that's definitely a strong value proposition. You wouldn't put up there if you didn't believe in it, right?
Right.
So about that Monte Carlo simulation topic, I think we could shift gears a little to it. So do you want to talk a little bit about what it was like setting that up for Goldman Sachs? But first, we'll I guess maybe talk about what Monte Carlo simulation is, if you want to maybe give like a little high level for listeners who might not know.
Yeah, of course. So, Monte Carlo is one of these tools that big banks, big investment banks, and insurance companies use quite a bit to essentially price out, to figure out what is the likely price at some future point, right, of some risky asset or some financial instrument whose price is fluctuating with the market. So its future price is really unknown, right? So they run a lot of different simulations under a lot of different scenarios, and then essentially they take an average and a confidence interval around that average, and that becomes their informed guess as to what that asset's price is going to be in the future, right? And so for simple assets, it's easy to do that, and it's easy to maybe do these simulations, and you need to do a lot of these simulations to have interesting confidence intervals and really interesting averages. But maybe for more complex assets, it becomes harder and harder. You need to do more and more of these repeat scenarios. You need to run more of these scenarios effectively to come up with a good accuracy of your average and a tight confidence interval around that average, right? So what typically happens in these banks, and again, this applies both investment banks, potentially retail banks as well, maybe to a little bit lesser extent, and also all kinds of insurance companies. They typically essentially run all these simulations typically on GPU platforms overnight. These are calculations that typically take hours and hours on end to complete. And then once the traders come in the morning to start trading, they have the results basically from essentially last night's run. So the potential value proposition here for quantum computing to come in and address this this area is for quantum computing to essentially execute this calculation faster than what the current classical infrastructure can, and maybe can become as faster than what they're currently doing, and as fast as to be able to essentially do it throughout the day, as opposed to doing it once overnight. With a quantum computer, potentially in some time in the future, you might be able to do it sort of many times throughout the day, so that the traders have the latest information in front of them at any given point within the day, especially when that day might be very volatile and you might have different things happening in the market.
So what kind of hardware did you use as the back end for this?
So so we started working with Goldman initially. So we've had this collaboration with Goldman, which is public now. We've done multiple press releases. I think that our first press release we did was back in December of 2019. And then the latest one was maybe a few months ago. So initially, when we started working with Goldman on this, it was to prove out essentially the theory, to prove out that we can, in fact, work on an algorithm that improves the speed of doing these simulations. And not only that we get faster results, actually, that was a result that was already known for some time. There was already researchers that had proven out that quantum computers will be able to execute quantum Monte Carlo simulations faster than classical computers. However,
like 2015, I think. Yeah, like around 2015, they kind of proved that, yeah. Mm-hmm.
Yes. But the problem with that result was that the computational resources needed to actually run that algorithm were so high. The quantum computer needed to actually run that was so large and had such high demands on fidelity and qubit count and everything else that analysts expected that a quantum computer that essentially was going to be able to handle this result was only going to be available essentially 20 or more years into the future, right? Because you needed a lot of qubits and you needed a lot of high quality qubits to be able to run this initial algorithm. So our initial collaboration with Goldman concentrated on how do we get the benefit, how do we get the result, the result that we need, while at the same time minimizing the resources needed to actually run this algorithm. And as a result, if you minimize the resources needed to run the algorithm, you can essentially bring the time frame closer. You can bring the time frame for this algorithm to have an impact in the market from 20 years, maybe to 10 years, maybe to 5, maybe sooner. So we started working with Goldman, and the first essentially 2 years, we worked on the theory of how to essentially get the same results with fewer resources. Actually, there was also a trade-off there, right? So to be completely transparent and highlight this for your listeners, is we had to trade away some of the benefit to significantly reduce the resources. So instead of getting the full benefit of the quantum algorithm, as it's described in that initial paper, we can get maybe 80% of the benefit by only using maybe a much smaller 1/10 the size of the previous computer that was required. So these numbers are kind of rough. Don't kind of quote me on this. I'm just kind of giving the conceptual example here. Mm-hmm. And once we did that, once we proved the theory, then last year, we also went to one of the hardware vendors. And so we had this three-way partnership between Goldman and us and IonQ, actually. That was the hardware vendor. And we also executed on hardware to make sure that the theory checks out. The machines are now getting to the stage where they can run some of these calculations. And we do get the results that the theory says we're going to get and we get the performance that the theory says we're going to get. So the latest press release actually that we did with both Goldman Sachs and IonQ highlights the fact that we completed that. We also published the results in a paper that's on the archive now, and so we kind of have confirmation that we're on the right track.
Yeah, and I'll link all that in the show notes, definitely.
Great.
So what's terrific there is when that paper was written, the IonQ machine didn't exist, and algorithmic qubits didn't exist, like what they're considering good quality, and everything keeps changing, and it's all about squeezing that extra little bit, as you know, from the stack, like some from the hardware, some from software, some from the approach. So that's it impressed me, the way you're able to kind of throw that on its head and actually get something usable in the short term. And and we've seen that before with other things, like with portfolio optimization, we get better speed, but not as good a Sharpie ratio or whatever. There's always some kind of trade-off to show some kind of quantum edge right now. Hesitate to use the word advantage because I don't think we're quite there yet.
Yeah, it's definitely not advantage. I mean, we have to be very clear. I mean, I think I forget exactly what kind of derivative they priced, but it's something very simple, something that a classical computer can basically do like in fraction of a second. So you can't even compare, right? You can't even benchmark right now. I mean, these things will become relevant when once we have a lot bigger quantum computers and they can perform computations that the current classical computers literally take hours, right? That's when the benefit will become apparent. Yeah. But right now we're definitely not at that stage. Yeah.
And that's, of course, the whole concept of quadratic speed up, right? From everything you did, are you feeling that we're on track for quadratic speed up? That it's charting, it's showing up as what's going to happen?
So right. So I think all the results that we're getting over the last few years are very very encouraging, and both on the software side, but also on the hardware side, right? So we have these big milestones from the hardware guys being achieved, and also we have these results on the software side also that keep reducing essentially the resource requirements to get to practical results, to advantage, right? I think the biggest thing for me right now is to essentially see whether the hardware guys can stay on the roadmaps that they have published, right? So now we have published roadmaps basically from IBM and Google and IonQ, and it's important to see how close we can stay to the published roadmap. Maybe there's going to be a little bit of a deviation. That's fine. I think it's a little bit, but if 2 years from now, let's say we're still talking about this thing being 3 to 5 years out, then it's not going to be good if that happens 2 years from now.
Yeah, 3 to 5 is that magic number I've been hearing since the beginning, right?
We have been using it for quite a while now. Yeah, we've definitely been using it. I feel for sure. Maybe we started using 3 to 5 years, maybe 2 years ago, maybe a year and a half, something like that. Yeah.
It's a good catch-all, and so you partner with Goldman there on this, and I'm starting to think of them as like trying to be, I guess, second place to JPMC when it comes to quantum innovation. JPMC, it's no secret. I think they're like sort of the leader in the space.
Right.
So what was it like having a customer that's that aware, right? Did you have this enormous team to work with there that were really, plugged in?
Right, right. That was definitely. I think it was definitely easy on the one hand because you didn't have to go with value proposition. You didn't have to go with the why
Hmm.
quantum now, even though it's far away. I mean, all these questions kind of were answered. I mean, they've already made the investment. They're growing their team. I think it was also interesting for our research team, our own team, that they could just go in there and kind of have very high level or well, maybe high level is kind of the wrong word. It's basically to the point conversations, right? They didn't have to start from scratch and kind of build them, kind of educate them. We could go in and kind of go and start discussing really the details of how to proceed, how to kind of push the boundary. So I think both on the business side and on the technical side, it was a pleasure because of that high. Um, Essentially high level of the people on the other side for sure. Yeah.
Excellent. And soon anyone will be able to play with this exact setup. Well, almost, probably not exact setup, but
Yeah.
similar
Yeah.
inside of
Exactly.
Forge.
Exactly.
And so is there a project then that's not quite public yet? And you obviously don't have to reveal anything, but is there a project that is going to be the basis behind the chemistry simulation, like some real world cutting of teeth with with a partner to back that
Right.
piece up?
If you don't have to read too well between the lines. Actually, it's almost out there. If you actually just go to our website and look at kind of the research we've been publishing with other groups, right? So
Hmm.
you'll notice that within the last few months we've published papers with um, uh, the pharmaceutical company Roche on this biomedical imaging, so which is basically image classification. So
Hmm.
that's more on the QML side. But we've also published a paper with Covestro, the German materials company, um, and where we do chemistry simulation there to discover properties of molecules for materials. And we also published some work with a team from Boehringer Ingelheim, the other pharma company, again on molecular simulations and more. It has to do more with drug discovery or essentially affinity of drug binding. So if you I mean, again, this is all the papers that are there, right? I'm
Hmm.
not revealing anything new.
Oh yeah. When I
Uh,
ask a question, sometimes I know the answer, but yeah.
yeah, exactly, exactly.
Yeah.
So if you see all that, obviously, yeah, these are kind of the algorithms that are at that stage where we've worked essentially with these large customers. We've discovered interesting results. Now we publish the paper, and then these will make it into the product in due course, right? I don't want to say. I don't want to provide a time frame on that, but that's definitely that's the model, right? I mean, take these
Yeah.
results and kind of distill them into a usable form for everyone. Yeah.
I love it. I think that's such a terrific approach. Anything you like log into and try, it's been done. It's great. It's
Exactly.
not
Yeah. Yeah.
theoretical.
Yeah. We try to do actually, if you go to the Forge website, you can see under pretty much every feature, we say which paper this feature is actually based on, right? So you can actually read,
Hmm.
there's a link on the documentation, obviously, but there's also a link to the paper that describes basically, okay, well, what's the advantage of using this feature? So we have, for example, a feature that talks about, just doing linear algebra, right? On quantum computers, just doing essentially calculating distances and calculating matrix multiplications. And on the website, we say, okay, well, this is the feature, and this is the paper that exposes why this feature is going to be faster on quantum computers rather than classical computers. So kind of everything that we do is very comes really from fundamental research that we've done either on our own. Some of it is entirely internal. Some of it we've done on our own. Some of it we've done with these large corporate customers.
Yeah, that's terrific. It really is a good way to lay it out for everyone to see. And I guess one last thing I wanted to ask you. So you've done these kinds of use cases. You've obviously tried to figure out what the impact will be in time, given more power, whatever. So if we stay strictly in the gate-based world, what
Mm-hmm.
do you think will be the first application, in your opinion, that might actually be able to earn that advantage word? Everyone seems to have a
Right,
different
right.
opinion, so I figured I'd get yours.
Yeah. Yeah, most people think it's optimization. Well, so sorry. Actually, are you asking the context of finance,
Or any one of the use cases that you've tried in just the gate-based world. Because in annealing, I feel that's optimization for sure, right? But in gate-based, what do you think it's going to be?
Right. So then it's definitely going to be something in chemistry simulation. So we're convinced of that. The teams believe strongly in that. And we expect that there is a chance that if the hardware stays on its current course, we might be able to do something in maybe 2 to 3 years, have a very specific use case that demonstrates for that specific use case. There's not going to be a very generic result where it's going to be, put your molecule in a quantum computer, you're always going to get better results or faster results. But for certain molecules, certain properties of molecules, you will get that initial use case and that initial problem instance in chemistry simulation. And we do expect that to happen in the next 2 to 3 years.
Nice. Okay. We will start boning up on chemistry. No.
Exactly.
Yeah, that's terrific. Thank you very much for joining. And I'm excited to see how this evolves.
Thank you so much. Thanks for having me.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. QC Ware's team is developing practical quantum use cases based on original research, as well as other scholarly papers. This approach lets the company prove the effectiveness of algorithms and applications in the field, and then offer them to customers as ready-to-use building blocks of code. These applications become available through a tool called Forge, which has enterprise-class features and should make development easier for those new to quantum. QC Ware seeks to let data scientists do what they are best at, without worrying about which quantum computer they'll be sending their new code to on the back end. One of these use cases that generated some press for QC Ware is Monte Carlo simulation. These have been around for a while as a risk tool on classical computers, and let companies run simulations of how pricing might change. Since around 2015, researchers have believed that quantum computers would one day be able to perform Monte Carlo simulations in a square root of the time taken by a classical system. QC Ware has been able to prove to Goldman Sachs that this will be the case as quantum computers become more powerful. Reusable code for this approach will soon be available in Forge, where it will join other field-tested use cases already in the tool. Despite the press around Monte Carlo simulations, Yianni thinks the first advantage in gate-based quantum computing will come from chemical simulations. This is a nice full circle to 1981, when Richard Feynman proposed a quantum computer to simulate the quantum universe that we live within. That does it for this episode. Thanks to Yianni Gamvros for joining to discuss Forge and the use cases QC Ware is tackling. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.